Alright, time for other DraftPhysics.com. DebatePhysics.com also, video presentation. So, I will read a physicist, Michael, comment. And in some sort of fairness, he apparently covered all bases. I mean, he predicted everything, it seems, in some place in a video. So, but we'll go to his predictions and we'll talk about the facts, what we're supposed to think his predictions actually are. And it really doesn't make any sense, and so I'll get to the first part of it. I might as well just do it and be done with the argument about direction. So this whole idea of, he in one place he makes it clear, I set up a simple experiment. I say, okay, we're just going to do a lever, we're going to just drop an object on this side, and the same object over here, same distance in the fulcrum. What happens? I didn't say anything about sticking, I didn't say anything about any kind of crap. I just said, look, you put the energy in this way, it comes out this way. And he said, no, it doesn't. It'll be half here and half here. And this is a reflection. It's going that way. This is going that way. They're going the same direction. Glare again. Good enough, I guess. So, what I've tried to, what I have pointed out, frankly, and I'll make it really clear this time, is there's only, there's two things that can happen in this experiment. You put the energy in, and something comes out over here, okay? And you get a reflection. Some of the energy comes back this way. That's if this is out here, far. If I move this out further, I get a bigger reflection this way. If I move this in closer, then it starts to go this way. Okay? So it's a clear difference. You're either going up in a reflection or down in a reflection if any of the energy stays over here. And it's just kind of obvious that between this positive direction and this negative direction, there's a zero. So there's some place where you have this object where it weighs the right amount and this energy is completely transferred to this object. But you can't, there's no other way for it to work. There has to be a zero somewhere between these 2 points. It's not either this or this, it's also this. Nothing. It doesn't move. Alright, so we know what they're saying can't be true because there is that place. So if you find that place, there's zero reflection. Alright, so I shouldn't have to keep going over that. This changes its weight. Moving something this way or this way changes its weight. If you make it lighter, then you're going to get energy to continue down this way. If you make it heavier, then you're going to get reflections. Shouldn't have to say more than that. That we should both be able to agree. There shouldn't be a disagreement about that fact. Alright, so to the comments. And we'll show his one of his statements, okay, about his predictions. But again, I've played the clips. Alright. So, I'd be advised against using DS comments for anything other than what he thinks will happen. Well, I'm attempting to understand what you're claiming will happen. And the fact is, you directly told me it can't do what I suggested. And you said it has to do half this way, it has to do half that way. That's what you said. Now, I think the misunderstanding is your misunderstanding. Not that he's listening. But let's just understand that this word elastic doesn't mean anything, okay? Because there's this condition where they're saying it's inelastic if it sticks. Well, if it's a hard object and it sticks, it's still elastic. Elastic really means, in my opinion, whether it's deformable in a permanent way. If it's not deformable in some permanent way, that is, it doesn't fall apart, or you don't move pieces of it in a permanent way where they don't come back, that's inelastic. That's absorbing the energy. The object isn't transferring energy because it's the energy isn't staying in the objects themselves. It's being transferred into motion within the object. So that's inelastic, and everything else is elastic. Or whatever. His descriptions of the classical physics predictions are generally wrong. So again, you say they're wrong, but your crappy experiment didn't prove them wrong, because you wouldn't even do the experiment as described. If he says that the classical physics prediction for the 2x mass at half the distance, 2x at half the distance, is that the lever will launch the second mass at 1.4. Obviously, this isn't my prediction, you fuckhead. That's what the people you're with, that's what they say the prediction is. Now, he's saying it's 1.33. So, I don't know. Times the original. He's wrong, because that would imply that the original mass stopped. And it's clear that the original mass can stop. I mean, there's only two choices: reflect, don't reflect, go straight through. So what do you think happens? You go automatically from zero reflection and you automatically have what, all passing through? No, it starts with zero. It goes through zero. Okay, no energy available, and that the configuration would violate conservation of angular momentum. So let's just read again. He's wrong, because that would imply that the original mass stopped. Yes, I'm stating it can stop. That is a possible option, is to arrange the experiment in such a way where the original velocity in stops. It doesn't reflect and it doesn't push through. No energy available, and that configuration would violate conservation of angular momentum. So again, it keeps talking about angular momentum when the experiment is on linear tracks, which is just, somebody besides me should call bullshit and just say, will you quit talking about something that has nothing to do with the experiment? Because clearly the carts, which we are trying to put the energy into, are moving linear paths. This has nothing to do with any angular momentum. And angular momentum is the key property that conserves any of these lever collisions. So again, says him. Alright, and somebody, him for example, should explain why I should give a shit about the angular momentum. Why I should care about what the lever's doing when I'm trying to minimize its interaction in the experiment entirely. For the 2x mass hitting at half the distance, so that's the same one, the elastic case. So again, he says the word the elastic case. He's saying elastic is a spring, when obviously Newton's cradles are elastic and there's no springs. So obviously there is an elastic case that isn't a spring. So it's again just sort of bullshit. Well, it's not sort of bullshit, it's entirely bullshit. This is bullshit. This is gibberish. Alright, to sit there and play this game and say you have now defined elastic as, well, if it doesn't have a spring, it's not elastic. Bullshit. Would predict that the original 2x mass will bounce backwards. Okay, that's basically saying because the other mass, the lighter mass, is too heavy somehow. So let's draw it. I mean, I know some of this will be insanely redundant for some of you, but let's just be clear that this is the simple experiment that none of us have, 3 people doing it and nobody's been able to do it right. Now Brozo did do it with billiard balls, and he got pretty close to a 2-to-1 outcome. 19 and 11 would be the frame rates, so pretty close to 2-to-1, and not very close to 1.33. Okay, so anyway, this is the simple experiment, right? So fulcrum, you have a 1 mass out here, and you have a 2 mass here, and the 2 mass is where you're introducing the energy. So this will have a mass and a velocity, and this will end up having a mass and velocity leaving. And the trick is, as I'm pointing out, is we know that if I push this out here further and make it heavier and heavier, I get more and more bounce. And if I start to move it in closer and closer, it gets lighter and lighter. It gets easier and easier to push. Okay, and this, instead of bouncing, because it's going to have leftover energy, it'll take less energy to move this. So I put a one mass equidistance. It's going to be really easy to move that one mass. And it's going to leave at this limited though velocity, because you're not here on the lever, you're here on the lever. So the velocity will be down. Okay, and so this will have leftover energy. And the leftover energy isn't going to bounce. It's going to plow right through the lever. So those are really, you have two choices, this or this, and there is a place right here, okay, where neither this or that will happen. This will hit the lever and essentially stop, and this will presumably have all of the momentum, minus what the lever consumes. That's the simple argument. Why it has to be made complicated, I don't understand, except obviously they're trying to evade the subject. Why make it complicated? I've said it over and over again. How could people confuse what I'm saying? Alright. So here we're back again. Okay, for the 2x hitting at half the distance, the elastic case would predict the original 2 mass will bounce backwards with 1/3 the original velocity. So even though technically the 1 mass weighs exactly the same as the 2 mass, that is, they're balancing. Okay, so if I put them on a balance, they will balance at those distances. So the 2 mass close, the 1 mass far out weigh the same, but somehow it's going to bounce back with 1/3 the velocity, indicating that somehow the 1 mass is heavier. All right. And the second mass will be launched with 4/3 the initial velocity. So 4/3, I would say, is not 1.4, right? That's 1.33. So his prediction is we've now changed the number from 1.4 for whatever reason to 1.33. Okay. So that's the new physics. That's what the doctorate in physics says. Okay. And he gives a link to the time code of his predictions video, where he has it all written down. Frankly, I didn't pay enough attention to what he had written there. This assures that the bar is massless. This assumes that the bar is massless. We already know it's not. So we know that the 133, by his own experiment, we know we're losing something like 90%. I mean, we're putting this in, let's say, at the same place each time in the same way, basically, and expecting certain percentages out. So you could argue that it's going to be about the same amount used up by the lever each time. The lever's not going to use different amounts of energy, consume different amounts. So it's going to be somewhere around 10%. So you know that this 33 is going to be 122, 120, because it's going to lose 10%. Alright, so we're not going to assume anything's massless. So let's be realistic and understand that, yes, you're going to lose about 10% total momentum to the lever. And you just have to figure out that, yeah, you're probably going to lose it in both sides. But anyway, it doesn't matter. So with a realistic bar, 1 meter will bounce back a little faster. M1 will bounce back a little faster. And M2 will be launched a little slower. So again, it doesn't make much sense to talk about them being launched when it's a reflection. Okay. I need actual masses of everything to make specific predictions. So no, you don't. You just pointed out that the formula says something. You can do the figuring. I mean, we already know it's about 10% for the lever. Don't we already know that? Yeah. I think we already know it. Alright, so let's go to the link. That's not the right link. This should be it. Okay, so I guess I'll try to blow this up so we can all enjoy the predictions properly. Alright. So there they are, and it's just plainly wrong. Okay, so I'll go over it. It's duplicity on his part. Okay, now in the first place, he writes this in a really strange way. He says if m1 equals m2, or if m1 equals 2m2, instead of just saying m1 is 1 and m2 is 2, just make it simple. Okay, you have to figure out that what he's really saying is m1 is 2 of m2. So m1's the heavy thing, and the thing with the front 2 in front of it is the small thing, which is just really irritating. All right, I mean, just frankly, okay, that might work for him, but it doesn't, it's saying it backwards. The 3 should be where the thing that's heavy is, not the, anyway. So you have to invert the numbers to recognize what he's talking about. Anyway, and then the r equals r, I guess that's okay, but saying 2r, just say twice the r, r2 equals 2r1, so now you have to recognize, oh, I have to flip the 2's over here. The r2 is the far r, okay. And then here is the magic part, right? Because here's the case. I'm on the inelastic? I thought I was on the elastic. Alright, well anyway, here's where he says the inelastic is where you get 1/2 and 1/2. Now, what exactly would be that inelastic case? See, that's we're left with nothing here. We know if you put clay there, you're not going to get 1/2 the velocity out. So we know clay wasn't what this is. I mean, that prediction would be totally unrealistic. So what exactly were we supposed to get this 1/2? So if we put Velcro on, would this, now we would be doing this formula? So I think Ian Gosling knows that, well, if he puts Velcro on, he's not going to get these numbers. I think he knows that. Not going to happen. Okay. It's going to be the same as the other circumstance, in the sense you're going to basically have 90% of the momentum on one side and 0% on the other side. Close enough to it. So this is just wrong. Must be another clip here. It doesn't appear to be. Okay. So I guess I'll have to jump, I think, ahead to get to the, might as well just do the elastic, these inelastic cases. So the inelastic cases don't really fit for anything, right? And he also, there's signs here, so in this case, so just recognize in this case he has 1/2 and 1/2, and they're both positive. So that means they're both going in the same direction. And he's calling that positive because there's no minus signs here anywhere. So these are all positive directions. Correct? All right. And but when he gets to the inelastic case, that's all going to change. Maybe it'd just be easier to hit the link out of here. Alright, so this is for the inelastic, I think he said. The elastic case. Okay, so these are the elastic cases. It says inelastic again. Alright, so I'll have to jump to the other clip. So for whatever reason, he's talking about the elastic cases and gives me the link to the inelastic cases. I don't know how that happened. So these should be the elastic cases. Hope. Oh, come on. How can both clips be the same? They can't be. Alright, I must have did something wrong. This is 1716 in the video. So this should be the elastic case. Oh, fuck. How is that possible? I mean, something's... I guess I'll have to pause to figure out where the hell did the elastic case go. So that one's at... That one doesn't have a time code. This doesn't have a time code either. I wonder why. Why did they take away the time code? This looks like 17 whatever. So we have to go back to like here.
That axis.
Alright, here's...
And now we have two equations.
Okay, we have two equations and only one formula. We can't do anything. So we're doomed. Alright, let's see if we can get all the formulas on one page here. There they are. Okay, finally. Sorry about the trouble with the links. So you can see that. All right. So these are his real predictions, let's just say. So this is the one he wrote it all down, so this is the serious part. All right, so M1 and M2 are the same. This is the same mass, same distance. And he has them one side with nothing, 0, which is the way it came out basically, and the other side gets all of the velocity. It has the same velocity as the thing coming out, so we've conserved most all of the momentum. Now it comes out the real numbers are 90, not 100%. So we know in reality we're not going to get 100%. Alright, so here's where it gets interesting. Alright, so here's the one mass, two mass, twice the distance, blah blah blah. And he has the 1/3 with a minus sign. So he's calling this direction, this reflection, a minus. So he's saying this one bounces back with 1/3. And this one goes forward, goes this way, 4/3. And there's no minus sign. Can you see? There's no minus sign. They're going in the same direction, so by his own statements, direction matters. By his own statements, that's wrong. They should have the same sign. They're going in the same direction. They should have the same sign. So, again, just shenanigans. It's always some sort of game played. Alright, and the 4/3, again, what else can 4/3 be but 1.33? So that's our new target. Anything above 1.33, right? Because we're losing 10% to the lever, right? So, okay, so we're losing 10% to the lever, so you know that number has to be, you know, the outcome will be something like 1.25 or something. So we're not going to get that 1.33. So, and clearly the experiment, his own experiment showed more than 1.25. So he's already in trouble. And he didn't do it right, frankly. So if he does it right, then, you know, you have a much higher odds of getting the right numbers. But anyway, so it's clearly he's playing a game with the signs here. So as much as he talked about how direction matters, he's proving it doesn't matter when we don't want it to matter. So when I can't make sense of it, I'll just forget about the signs. Okay, the signs don't matter anymore. Alright, and then for the 3-to-1 case, he has 3 halves. Okay, so 3 halves isn't that much more, right? I mean, 150 isn't that much more than, you know, it's not much more than 1.4, right? I mean, 1.4 is right in between those two. Well, you can't see what I wrote. So that's kind of a funny thing to say, right? Because it's a whole another unit of mass. And you're not going to gain much in velocity by his claim. So even though it's 1/3 is light now, and it's 3 times further out on the lever, it's only going to move with a slight increase in its velocity. So the reflection will be 1/2 the initial velocity. So we know that only, in my opinion, half the energy could possibly get to the other object, and yet with half the energy, it's going 3 halves. It's going with 150% of the original momentum. So that's not going to happen. But anyway, so those are his real predictions. Apparently, those are the ones he'll stand by. Those are the written ones, and the signs are wrong on all 3 of these. I mean, you don't need a sign on a 0, so we'll give that one away to him. But clearly here, these reflections will be in the same direction. Okay, so the direction of the reflection is the same as the direction of the motion here. So he's just playing a game here to make it work his way. So he can say this minus that equals what you had originally, when it really won't, because you put in this way and you got all this way back. So, you know, it's easy to call bullshit on that. So I will. I'm calling bullshit. Alright, so we'll go back to reading the original comment, I guess. Not much more left. I mean, it just talks about the inelastic crap, which nobody suggested doing an inelastic experiment that I know of. No one could have cared. Who wants to see something break? That's not what we're interested in. We don't want to see something break or something deform. or something squish. Alright, back. So, third paragraph. Alright. Let's see. This assumes that the bar is massless. Okay, none of that is realistic. It needs actual. Okay. For the 2/3 velocity prediction, that was the case for the completely inelastic collision. So there's the link too. And again, this completely inelastic, whatever that even means, completely inelastic. What does that mean? So clearly, he's claiming, all right, that no sticky stuff, no spring, just hard object against hard lever. He's saying would fit that description. Yeah, but clearly it doesn't. Okay, so he's wrong in that understanding, clearly. So if the masses collide with and stick, well, what is and stuck? What is this stuck part? Stuck means they don't leave the lever and they just stop pushing to the lever, then that was the predicted outcome. So the predicted outcome was half and half, and obviously it doesn't come out that way. Alright, the clay I used for the bumper definitely didn't cause it to stick to the lever. Yeah, it didn't do anything useful at all. It was completely useless as a mechanism. Okay, it still had considerable bounce. Well, how much bounce it had doesn't really matter, because what it really had was compressibility, and it just compresses and moves the clay to a new position, and moves the clay molecules to a new position, and essentially disperses the energy as heat. So it wasn't that the prediction was demonstrated to be wrong, but it certainly was by Ian Gosling just now. I mean, he proved it to be wrong by just banging the metal ball into the lever and having most of the energy, 90% of it, go into the other object. So obviously it was proven wrong by that experiment that he did that you didn't do. Okay. And certainly my own setup did the same thing. Okay. It's that the setup he had couldn't get the completely inelastic part of the collision. So again, he keeps talking about nobody wanted to see an inelastic collision, whatever the fuck that is. Okay, so that the specific prediction is untested. I mean, this idea of hard things sticking, again, is illogical to say that that's inelastic. If nothing gets deformed permanently, you can't call it inelastic, because there is no reasoning for you to change anything in terms of how the energy is dissipated. It has to stay in the two objects. Okay, what we could verify is that each trial did produce outcomes between the extremes. So he wants to see between the extremes of elastic and completely inelastic. Those extremes are 100%, as you're pointing out, or at least 50%. I mean, that's a gigantic latitude you're giving yourself in terms of a result. So he's saying basically I can come up with 1/2, anywhere from 0 to 1/2 is fine, or anywhere from 1/2 to 100% is fine. So anything between 100% and 50% is fine. I win. That's a good prediction. No, it's not. It's a shit prediction. 1/2 and 100% are big differences, and if your prediction can't be any better than that, then it's not very useful, your experiment. And that the angular momentum, so again, nobody was interested in angular momentum of the system, and he measured the angular momentum of the lever after the objects left, which makes no sense to me at all. So Ian, you want to explain to me why measuring the velocity of the lever after the objects have left is it of all interest to anybody? Why anybody should give a shit? How that proves how fast the carts are going, which left the lever? They left. They're obviously not going the speed of the lever. So why do I care how fast the lever's still moving? That's certainly not the system. You do understand that's not the angular momentum of the system. After you've thrown the two objects off the lever, I don't think you can say the angular momentum of the system is now going to be represented by what the lever's still doing. So what a pile of crap that is. That's just gibberish. was conserved to a high accuracy. Again, what was conserved? He's just basically saying you lost the same amount of energy each time to the lever. How can the lever not conserve the energy in a sense, right? I mean, one side of the lever has to move the same as the other side of the lever. So I can't make any sense out of that. So if somebody understands what the fuck the angular momentum of the lever after the objects have left, what that has to do with anything, explain it, because I have no clue what you're talking about. The carts are on linear tracks. They don't have any angular momentum. Again, it's the angular momentum that is the key for this lever experiment. Absolute bullshit. Just garbage. Crap. Shit. Alright. So, I mean, the Watto's stupid comments. Why bother trying to understand the Sphinx? Whatever. Let him do the experiments himself to demonstrate what he claims will happen. Again, well, I've already proven that that's what if I have to do it, then I'll do it. Okay, but I don't have interest in doing experiments. I don't have facilities for doing experiments. If this is the way you think physics should be done, okay, is on basement floors, I mean, fuck. I don't think you have a very high degree of respect for what physics should be. Now, you know, I mean, physicist Michael has said these experiments have been done. He just doesn't have the references. Well, can you find the references? Can somebody come up with a reference and then we won't have to bother? I mean, it seems logical that science somewhere would have played with a lever and figured out how it works. So why don't you just tell me how it works based on what, you know, some other person who's done this science? Again, you don't have any of this evidence, and you're just sitting here talking as if I have to go out and prove that it doesn't take 9 times the fuel to go 3 times as fast. Don't you think you should have had to prove that? I have to prove it's not true. You don't have to prove it is true? I mean, it's such duplicitous hypocrisy. But he prefers to sit on his throne. So I'm obviously not doing any throne sitting here, right? I mean, I'm desperately trying to get somebody to provide a counter argument that's on the subject. You won't do it. You can't argue this. You won't explain to me why I said something wrong here. I mean, let me do this one more time, right? I mean, I can do it in 5 minutes. Why don't you sit there and provide me the explanation of how what I'm saying is not how it's going to work, not how it has to work. There's no alternative but it to come out the way I'm saying. Is there some possible alternative way it could possibly happen? I mean, I have the lever and I have a fulcrum. All right, I'm going to put this in here, okay, at a certain velocity with a certain mass. And now I'm just going to sit there and say, okay, I can put a light mass here. What do I think is going to happen? All right, well, I'm going to say, well, this is lighter and it's the same distance. Well, this has to keep going because there's no way this can go any faster than this was going. This part of the lever will move a certain speed. This part has to move that speed. This goes off with the same velocity that had at best. And this is going to have a whole bunch of extra momentum, so it's going to plow right through. Is that or is that not going to be the result? And if I go out here, now this weighs 4 times as much, let's say, as this. This can't, for a small thing banging into big thing, well, we know what we're going to get. We're going to get a reflection, so that's a known fact. Absolute guaranteed reflection, because the energy just can't go in here. It's too heavy. It can't make it move that velocity. If it won't go, if it won't budge, just like this fulcrum, it has to reflect the energy. Can't budge something, then the energy has to be reflected. If the wall doesn't move when I throw the ball at it, or whatever I'm throwing the ball at, doesn't matter what I throw the ball at, right? If it doesn't move, then the ball has to reflect. So, no. What's complicated? So we know we're not going to get barely any velocity into this object, and we're going to get a huge reflection. And we know that there's some place right in here somewhere, right, where I can put the object where I'm not going to get any reflection, and I'm not going to get any going through, and it's going to be 0 movement here. And I don't have much choice but for all the momentum to go into this, because none of it's still here. So if none of it's still here, I got 10% in the lever, then the 90% has to be here. Now, is there some other way it can come out? Explain it to me. You can't do this and explain how something else could possibly happen. I make the object lighter, this is going to plow right through. I make the object heavier, this is going to bounce off. And we know there's something in between. Shit. Not that complicated, really. Alright, so we'll call that a video. I have a headache. All this bullshit. I mean, it's just so simple, and we can't get it, somehow it can't get done. Oh, fuck. Amazing. Alright, so, till the next time, and such, and so forth, and whatnot.